So we're going to be looking at homogeneous catalysts and seeing how they work to reduce activation energy. As before, just to be clear, because it's a catalyst, it will of course reduce activation energy. So steel as a catalyst reduce activation energy, and therefore, by reducing the activation energy, they lower the barrier required, so therefore increase the number of successful collisions, and therefore reaction rate, as all catalysts do. But they do this by basically creating an alternative pathway to reach the products. In other words, instead of going from A to B, which might not be as easy, what you do is you go via something else. So before, analogously, you've got A and you want to go to B. And let's say, A is Sydney, and let's say B is, let's say, London. Now, you know what, let's not say London, just because, let's say somewhere like, hypothetically, let's say Shanghai. Now, you can obviously buy a ticket direct. Now, it depends on the situation, and in normal circumstances anyway. Obviously, right now, that might not be as easy as normal. And to keep the numbers simple, let's just say, okay, you want to fly directly there, it costs $1,000. Okay? So that is kind of like your EA without a catalyst. But what a catalyst might do is it basically allows you more options. So a catalyst C might be a place like Hong Kong, which probably is under, or Virgin Australia, or, it's basically giving you more options and says, well, you know what, we can actually give you some specials, right? If you go to fly to Hong Kong first, and then, of course, you don't want to stay in Hong Kong, your aim is to get to Shanghai. So imagine this is Hong Kong. Then what might happen is they might say, well, it actually is not that hard to get to Hong Kong. It might cost, let's say, $300 ticket. I know that's unrealistic, but given the current situation, maybe they're on special. And because Hong Kong to Shanghai is really close, that is actually really easy. So we could, do that for $150. Now, this would be a massive difference. So let's make it more realistic. Let's make this like $700. And so if you go to A to B via C, do you still get to B?
Yes.
Now, does it cost more?
No.
No. So A to C to B, in my example here, would cost $850. Now, it still gets you to B. But if I went A to B direct, it would cost us $1,000. And basically, if C did not exist, so imagine if, Cathay Pacific didn't exist, well, then you can't fly to Hong Kong, right? It doesn't offer these flights. Does that make sense?
Yeah.
But because it does exist and because it does offer these flights, now the existence of Cathay Pacific, in my example here, means that you now have the option to fly to Hong Kong and then, do it that way. And this has now, in my example here, created a lower cost option than the direct flight. And that is basically how homogeneous catalysts work to reduce activation energy. In the sense that we often say a catalyst does not take part in the reaction, and that is not true. A catalyst does take part, a catalyst can take part in a reaction. So note, in this case, in my analogy, Hong Kong is the sort of like, catalyst kind of thing. it does take part. So a homogeneous catalyst does take part in the reaction, in the sense that it, the first reaction, A to C, it reacts, and then C to B, it will react again. But the key thing is, however, it will be regenerated in the process. So there is no net, no net sort of consumption of the catalyst. So what I'm saying is that for a homogeneous catalyst, it will react. So unlike what you might think, it's not that a catalyst doesn't react. A homogeneous catalyst definitely does react. It's, however, it's, it takes part in a reaction, in, for example, reaction 1, but it's then produced as a product in reaction 2. So overall, there is no overall change.
Yeah.
Now, I mentioned earlier that if we look at the esterification reaction, then what that would result in is, your concentrated sulfuric acid, in particular the H+ from the sulfuric acid, acting as a catalyst, right?
Yeah.
Well, what we'll do here is we'll give you another example. So an example is the ozone hole. Now, before, we polluted it with CFCs and so on, basically, short version is that the ozone was always going to deplete to O2 plus O as long as it got hit by UVB, and that's how it absorbs the UVB. And O2 will deplete to O plus O by absorbing UVC, which is a stronger one. And basically, you could just reform. And so this, this just, how much this happens and how much this happens just depends on the amount of UV. Does that make sense? And you can always get, O plus O2 to form O3. And so essentially, you can see that on the right, there's 3 O's. And so essentially, you can see that this will just form a sort of balance and equilibrium depending on the amount of UV. The more UV there is, the more oxygen atoms there are, and the less ozone and oxygen there is. The less UV there is, comparatively, the more, ozone and oxygen, all right? However, by introducing CFCs, what basically happens is, for example, Cl3F will hit with a UV, and basically, we don't need to care about it too much, but basically, you're going to get a chlorine being released. And this is a chlorine radical. And we won't care, so now this goes off and does its own thing, we won't care about that, we will care about this chlorine radical. So this chlorine radical, if it meets an ozone, because it's quite reactive, it will form a ClO plus an O2. Okay. And then another ozone might, for example, might absorb the UVB to form basically O2. And then you're going to get O plus, your ClO will regenerate your X dot plus O2. In other words, then, on your left-hand side, you're going to get Cl plus O3 plus 2O3 plus O plus ClO. And your right-hand side, you're going to get ClO plus 2O2 plus 2O plus X dot, or Cl dot, I mean. And you can see that this cancels and cancels. And those cancel. And your that one probably should have been an O2. So your first reaction here is the chlorine radical react with the ozone to give you the ClO plus O2. The O3, a separate O3, will absorb UVB to give you O2 plus O, which is kind of just this reaction here. And then a separate O can meet with the ClO produced here to regenerate your Cl, your ClO and O2. And if you look at the left-hand side, you'll get Cl plus O3 to give you 2O3 plus your oxygen radical plus your ClO, which produces your ClO plus 1, 2, 3 oxygen plus an oxygen radical plus a chlorine radical. And you can see that your ClO on the left and right cancel, and your chlorine radical on the left and right cancel, meaning that essentially, and your oxygen radical also cancels, meaning what has essentially happened is that this chlorine takes part in the reaction, but is also regenerated. So it's not used, net consumed. And what's basically happened is that chlorine here acts as a catalyst, essentially, for the conversion of O3 to 3O2. Because if you bundle all three together, essentially this is the reaction. And chlorine, essentially, by including chlorine in there, it increases and therefore catalyzes the rate of conversion of ozone to oxygen. And that's what's caused or significantly contributed to the ozone depletion problem. And this is an example of a heterogeneous catalyst.
Yeah.
Do you see how that works?
Mm-hmm.
So key thing, if we weren't looking at the details, we might just go it's ozone to oxygen. But if we look at the details of what the, like if we say, with chlorine involved, then it really means it's these three reactions. It does react, but it also gets regenerated. It does produce something, which is also used up. So it does actually react. Therefore, it falls into the category of, going from A to C by B. It does reduce the activation energy, but it actually does take part in the reaction. And that is how a homogeneous catalyst is different to a surface catalyst, which doesn't actually take part in the reaction. It just provides the environment.
Yeah.
Great. So that might be a good place to leave it there for today.